Well, thank you everyone for coming to this presentation on how the internet works, which I know is a satisfyingly broad topic, but in the next 50 minutes, we'll make everyone an expert, including me maybe. A little about me, I'm Joelle Maslak. I've been using Perl for some time, although I'm sure there's people in this room that have been using it longer than me, but I've been using it since 5.001, that was 1995. Been using Raku since Christmas, which was, everyone knows, 2015. I'm currently a network engineer at Netflix. I'm not going to talk too much about that, but if you have questions for me or something in the hallway, feel free to find me. I love talking about this. And because one of the best ways to get to know a tech person is to ask about their biggest outage. Mine was maybe 10 years ago at a tier 1 ISP. This was an ISP that bought a certain platform that one of the features of that platform was the same operating system everywhere. So the same operating system on the top of rack switch as on the big peering and customer routers. And so if you were in Texas maybe 10 years ago and you had a 30-minute internet outage, I'm sorry. I thought I was on a top of rack switch rebooting a switch for about a dozen servers. I wasn't. If you have questions during this talk, feel free to ask them. One of the disadvantages of doing something professionally, full-time, is after a while, you forget what is common assumptions and what isn't. So please help me out if I say things and you're like, I don't know what she's talking about, feel free to speak up. I'm going to start with a story. This is a story of two different internet connections. One is the one on my right, is a Comcast home internet connection that had a 30 millisecond ping time to m.routeservers.net. That's one of the top level DNS servers on the internet. That's great. The other one was some servers that I have in a half a rack I ran at a data center in Denver, 109 milliseconds, which, yeah, that's a lot worse than Comcast. So my question was, is my data center transit crap? What's going on here? And that's what we're going to dig into. And just a little more detail on that. Denver data center went to Paris. This San Jose is San Jose, California. So Comcast going California. So why is my data center traffic going all the way to Paris to get to this DNS server that there's obviously at least one instance of it in San Jose, California? Hopefully by the end of this talk, you'll be able to answer that question. So I'm going to talk about BGP, but I'm going to do it geared towards network engineers, or geared towards software engineers, not network engineers. BGP, Border Gateway Protocol, is the method that ISPs on the internet use to communicate what they're willing to carry across their network for other ISPs. When you're thinking of ISPs on the internet, and I apologize for the small text on some of these, you think of, from a BGP standpoint, BGP thinks of an ISP as something called an autonomous system. Autonomous system, all it technically means, a group of routers under common control with a common routing policy. That's an ISP, or it's an internet company. Each autonomous system, or AS, gets assigned a number. I've created a fictional internet with some fictional numbers here, and a server farm and a user that wants to talk to that server farm. One thing about BGP, and this will come up, you'll see it come up later, is each autonomous system makes decisions on its own. It doesn't necessarily know the decisions other people are making, other than these other networks have said they have a path to get to where I'm going. BGP has an algorithm. I don't expect anyone to read this and understand this. That's not what this talk is about. But there's an algorithm to decide which path you use when you have more than one path to a given destination. The one I'm going to start with is actually the second one, this least number of networks in the path. This is something that people will commonly think of when they think of routing protocols. You want the least number of hops. But it's not actually number of hops. It's not number of routers. It's number of autonomous systems. Each one of these clouds could have one router, or they could have 500 routers. You don't know how big that cloud is or BGP doesn't know how big that cloud is. But it does know how many ASs there is on a given path. So in this case, 65,004 has two paths to get to the server. This is the longer path. There's 65,003, 65,002, 65,000. So 3 hops there. Or it's got the shorter path, 65,001, 65,000. In this case, go and pick the shortest path to get that traffic to the destination, if we're counting number of hops. And likewise, in the reverse direction, same thing. But you always have to think, when you start thinking about networks, you always have to think bidirectionally. There's no guarantee that the two directions are the same, and in fact, usually they aren't. But you might have noticed there's something that's even higher priority than number of hops. It's this thing called local preference. How the selection rules work is each step, as soon as you find a difference between the paths, that's the step you stop at. So you only get to the number of hops if you get past local preference. Local preference is where policy is implemented. It's local, so it's local to the autonomous system, and it's their rules for how they want to route traffic. Money, that's what local preference really is. BGP is a money optimizing protocol. That's what it was invented to do. That's what it was designed to do. And it's kind of, local preference is a way you can codify these two questions. If you're an ISP, you want to make money by handing that packet to someone that will pay you to receive it. And you want to avoid spending money because you don't want to hand it to someone that you're going to pay to receive it if there's other options. And one of the things to remember on the internet, especially at scale, a lot of connections at scale, large capacity, unlike your home connection, are going to be metered. So the more traffic that goes across that fiber, the more money that will be exchanging hands. So if you've got someone that's willing to pay you more money to receive that packet and they've got a valid route to get to that destination, that's where you want to send it if you're an ISP. So I added the money here. Now, the one thing to realize is no AS knows necessarily what some other AS's business relationships are. They don't know who's paying who necessarily from the protocol, although there is some inferences we can make. But they do know who's paying them and who they're paying. I'll return to this diagram in just a second, but there's 3 kinds of relationships an ISP can have to other autonomous systems. They can be a transit, so that's someone that you pay to deliver your traffic. When I have my Comcast internet connection at home, Comcast is my transit at home. You can be a customer, which is the opposite of that transit. That's getting money from someone to deliver their traffic. Or you can have a peer. And a peer is no money is being exchanged. There's some kind of mutual benefit of exchanging this traffic. Usually that mutual benefit is avoiding paying someone else. So an example might be if you have a network in Western Brazil. You have 2 networks in Western Brazil, 2 ISPs. They could pay an international transit provider to connect between the 2, but that would be bad performing for their users and probably very, very expensive because Western Brazil tends to be pretty remote. So rather than doing that, they might say, hey, we're both in the same town, let's connect together. We can exchange traffic just between our networks so that we can both save some money. So that's what a peer would be. On this diagram, 65,004 on the bottom left uses 65,001 as a transit. They're paying that provider to deliver the traffic. They're also paying 65,003, so they've got 2 transits. This case, 65,001 and 65,000 on the top They're peers. There's no money being exchanged in this fictional internet. So with that in mind, and thinking about local preference, think about how the traffic's going to flow. And again, first choice is how do you make money? Second choice is least number of hops. So the traffic from this laptop, well, let's go and hit 65,004. It's probably part of 65,004. 65,004 has two paths. They both cost money, and we're going to assume that they cost roughly the same amount of money. So in that case, local preference isn't going to apply. It's going to go to that second criteria of number of hops. So it picks the shorter path. All is good. The reverse direction is very different, though, because this very first hop here, 65,000, it can send to the short path, but if it does, it doesn't make money for sending it. It probably made money from the servers. People running the servers are probably paying that ISP some money, but why get paid once when you can get paid twice? So instead, this would be the path that the network would choose. And in fact, 65,002 is actually paying to receive this traffic. So that's kind of a contract. They want to get that traffic. Now, in none of this, I talked about latency and geography. But latency is what a software engineer will typically care about on a network. As an example, if you have latency of 100 milliseconds to send a request to a server and get the response, and you have something that needs to be serialized, so you need to get that response before you can send the next response or request, then you can send 10 requests per second at 100 milliseconds latency. That's it. You can obviously send more in parallel if they're not serialized, but if they're serialized, and a lot of things have to be, you're limited to 10 per second. If your latency was 10 milliseconds, you can send 100 per second. And this has nothing to do with the bandwidth of the line or anything else. It's all latency. So that's usually what, when we're writing applications, we care about. The biggest determinant for latency is geography. It's the speed of light. Number of routers you go through doesn't matter. Number of switches you go through doesn't matter. What matters is how much fiber is in that path between your source and your destination. A good rule of thumb that I use professionally is for every 100 kilometers of fiber, you add 1 millisecond of round trip time to the path. So 1,000 kilometers of fiber, round trip time is going to be 10 milliseconds. So we're going to add some geography to this. And we're going to put the servers and the user in Australia. We're going to have a regional Australian Asian network. We're going to have some global networks in here. And then we're going to have a USA only network in here. If we want to optimize this for latency, we got a user and server in Australia. We want these packets to stay in Australia because every 100 kilometers, that's another millisecond. There's a lot of kilometers between Australia and the US. So there is something in BGP that's sort of related to geography. It's way down here. The smallest IGP or internal gateway protocol, that's the internal routing protocol in an autonomous system inside it. Essentially what this means is an ISP wants to get the packet off their network as soon as possible. Least amount of infrastructure they have to build is what they want to build. But that's way down. Local preference is still the top one. So we're still talking about how can we make money? That's the business that most of these organizations are in. So we have the geography. How does this packet flow from the user to the server? Does it go that way or that way? Well, it's going to go to 65,004. 65,004 then is going to look to see, do I have a path where I make money to send that traffic? No, I don't. Do I have a path where I don't have to spend money? No, I don't. So I'm going to have to spend money to get that packet to that server. So it doesn't matter which one I use from a money standpoint. Either way is going to cost me. It's going to go with the number of hops. So 2 is less than 3. So it picks that one. But again, money is the very first thing it looked at. On the reverse direction, It's going to take this path just like we saw before, but now we've overlaid geography. And this network, United States. So this packet is going to go through the United States on the way back. And in fact, 65,000 is going to get the packet in Australia. Well, it's got to get it to 65,002. 65,002 is only in the US. So 65,000 is probably going to transport that packet across the ocean to the US, hand it to this network, who hands it to 65,003, who's also in the US, but it's going to have to transport it to at least Asia to get it to 65,004. So in this case, this is very suboptimal from a user experience, but it's optimal from 65,000's perspective. I'm going to kind of go on a little bit of a tangent, but this is relevant here, and talk about how these interconnects work. I showed these ASs, these autonomous systems, only connecting in one place or one line. That's not really how they work. Everyone wants redundancy. How major ISPs usually do redundancy is multiple cities. If something happens in one city, they've got connectivity to all the ISPs they care about in another city. And I apologize for the super tiny text on this, but the important thing is you got the server on the upper left, the user on the lower right. You got two ISPs. The server is connected to the first ISP, ISP A in Denver. The user is connected to ISP B in Chicago. Both ISPs are in both markets. And so they've decided they want to connect to each other, and they have something called a network-to-network interconnect. That's just a telecom way of saying a cable between the two networks. That's where this comes in, because they're the same AS. It's the same two ASs, same AS on the top, same AS on the bottom, no matter which router it's using. But to determine how it actually gets routed off the network, it'll use the smallest IGP metric. And you can think of, you'll see cost used as a synonym for metric. Don't think dollars. Most ISPs, it's probably going to be based on either distance or latency, which is a proxy for distance. So when that user sends that traffic to Chicago to get to that server, the ISP-B, they want to get it off their network as soon as possible. That's using that IGP metric to do that. But essentially, they can hand it off in Chicago, and then the ISP-A has to figure out how to get it to its destination. That's good for ISP-B. The other part of this is ISP-B doesn't know where that server is anyway. It doesn't know that that server is in Denver. So it hands off to ISP-A and says, it's your problem. I'm getting rid of this, getting it off my network as soon as possible. That's what's best for my user, because if that server happened to be in Chicago and I carried it to Denver, that would be a problem. And now it's someone else's problem to deal with it. You'll hear this referred to as hot potato routing. The reverse direction is the same thing. The server hands it to the Denver router on ISP-A. ISP-A is going to immediately send it over to ISP-B, because that ISP doesn't know where that user is either. And plus, why would they want to carry it across the country when someone else can carry it across the country? And then I want to dive into one of those connections, like that Denver connection or that Chicago connection, and what do these actually look like? How do these networks actually connect to each other? And I'm going to show kind of three different models. This is the most basic model. This is the model that if you bought fiber internet from ISP, this is probably the model you're typically buying. You'd have an office building instead of an ISP on one side, but it'd be the same model, where you just have fiber between these two networks, connecting them directly together. Obviously, that requires construction and money and all of that kind of stuff. In addition to that, if you have a lot of ISPs, let's say New York City, London, Amsterdam, and they all want to connect to each other, you've got an n-squared problem. It's going to be a lot of money. So one of the solutions to this, and there's all kinds of solutions for all kinds of different markets, but it's a vendor-neutral co-location. So each ISP, and I just drew two, but there might be dozens of ISPs in this colo will have a cage or a locked rack or something in that facility. And rather than running fiber between ISP-A and ISP-B directly, and thus that takes some time, you would have a mess of fiber in the co-location center in the ceiling. Instead, all the fiber will run to a meet-me room, which is just a central room that's probably run by the vendor itself, so like an Equinix. And that vendor can patch whatever needs to be patched together in that room. So now you only have to do patches across a room instead of across a huge facility that may be even multiple buildings potentially. This is typically done when you still want that private fiber between the two networks. So it might be done when you're paying for a connection, because you obviously don't want anything shared. If you're paying for a connection, you want the dedicated fiber all the way, and this is dedicated fiber. No one else is on this link. No one else is on that link. If there's more than one person that needs to connect to the meet-me room from ISP-A, or you connect more than one ISP, you'll have multiple fibers between the rooms. But all the connections are made in that meet-me room. The problem with this is it works good for people that need 10 gigs or 100 gigs. It doesn't work so good for people that only have 150 megabits to exchange. Because then you're dedicating 100 gig or 10 gig router ports, you're dedicating fiber the whole way. That doesn't make sense. But I'll explain that in a second. This is what a typical meet-me room might look like in a co-location center. This one's pretty neat. One side of these racks has the cables coming down from the racks, and these are actually many fibers in these individual yellow jackets. That's the neater side. Then you have the other side, which is a little messier. That's going to be all the patch cables between these racks. So this is the third option. Instead of everyone having this n squared problem, even in the meet-me room, you could have everyone connect into an Ethernet switch. Everyone's on the same network. They can all talk to each other. This does have some maybe security implications. It also has implications of this line is used for everyone talking to ISP-A. So it's potentially shared and not dedicated and maybe congested if ISP-A is not managing things well. But this works really good when you want to connect to a lot of people and you may not have a ton of traffic to any individual ISP in that list. So ISP-A and ISP-B both have a connection to the switch. They can exchange traffic if they want. These are the three models. This one's usually used, as I said, for peering for smaller peering connections where people don't want to dedicate as much expense. All three are used all the time on the internet. You never know which one is going to be used, but this will come up with the story I gave. So now we're going back to our sample internet and talking about congestion. So we got that path from the server to the user, and we're going to say it's congested right here. Well, everyone's probably heard that BGP routes around nuclear war and all that. No network engineer said that, I will say. It does not route around congestion. If you look at the path selection rules, none of them in this list talk about congestion. In fact, our very first rule is still local preference. This network is paying $65,000 to receive that packet on that link. So that's what the network is going to try to do, even if it is congested. What can be done in this kind of scenario? Well, maybe 65,002 could upgrade their links and get rid of the congestion, but that costs 65,002 money. Maybe 65,000 could reduce their rate, so 65,002 wanted to upgrade. But really, at this point, you're kind of a stalemate and you're at the mercy of someone else. The server operator, about all they could do is buy a connection to 65,002 maybe. So what do you do about outages, or what does BGP do about that? This BGP does handle. I'm going to modify our sample internet. I added this link over here, and it's going to be a peer. And I added this link, which is a peer, so no money exchanging. And you'll see why I changed that in a second. So the traffic now from the server to the user, 65,000 has two choices. They're both peers. They both don't cost any additional money. It's going to pick the shorter one, at least from an autonomous system count level. So it sends it 65,001, sends it 65,004, gets to the user. All's good. Until a backhoe finds that fiber link. So now that connection's down. That might be one thing you think would happen. But in this case, who's paying for this at 65,001? They're both peers, so no money's being exchanged. So 65,001 isn't going to advertise that as a possibility to 65,000. They're not going to build out a network for people to use them for free. So instead, the traffic will end up going this route because 65,002 is still advertising a path to reach that destination. Everyone's getting paid by someone. Everyone's happy. But if another fiber gets cut, is there a usable path? In this case, no, there isn't. You don't want to be in this situation. Most ISPs don't want to be in this situation. So generally, this is the kind of thing network engineers think about and make sure doesn't happen, hopefully. It can be. So now I want to talk about Anycast and how we kind of put this into practice. This is kind of a traditional web architecture that you might see in an enterprise. And all these components probably have redundancies. There's probably 2 internet connections. There's probably 2 routers, 2 firewalls, 2 load balancers, and some number of web servers. And it's a fine architecture. Nothing wrong with this architecture. One of the limitations, though, of this architecture at a point is scale. Because these components in particular get kind of expensive to have big, huge firewalls handling, let's say you're dealing with terabits a second of traffic. That gets very expensive. So you might go to a model like this, where you put the firewalls on the servers themselves. Say we're going hard in the server, so it's as secure as a firewall would be. And then we're going to put a virtual IP that both servers have, the same IP address on both servers. And the servers are going to advertise that through BGP usually, but it could be another protocol, to a router and let the router do the load balancing. Because that's all going to happen in ASIC. It's going to be very fast. They already have the router, so they probably have the equipment to do it. It's got some limitations, but this might work for their application. So keep this building block kind of in mind. So this company built out this building block. They have it in the US server farm. They have a user in the US. Everyone's happy. The path for the traffic, the user goes to 3356, which bonus points if anyone knows who 3356 is. And then to 2914, 3356 for what it's worth is Lumen. It used to be CenturyLink, used to be level 3. 2914 is NTT, used to be Vario. And then to the server farm. So everyone's happy, and the reverse direction is the same thing. Until you have an Australian user. And now no one's happy because this Australian user is having bad performance connecting to a US server. Well, this company says, hey, we can take this building block, this Anycast building block, we can do it at scale on the internet. We can have that same virtual IP hanging off a server farm in Australia. Now we've solved our problem. And, well, you've solved a problem. This Australia user, they're great. They're happy. Performance is good again. But the US user is not very happy. Because, again, 3356 here sees one network that's paying it to receive traffic one network that's not paying it to receive traffic. So it's going to send it to the network that's paying. They want to get paid. And it just so happens that that virtual IP, this 3356 doesn't know that that IP is actually globally distributed. It's going to pick the best route to make 3356 money. So now your users are being served in Australia. I'm not going to get into the details on how you resolve this, but it's...
Is this actively making congestion for profit, this automated algorithm?
it could be. So yeah, I mean, and this is the kind of thing that a network engineer would address and figure out solutions for. There are solutions for this. Anycast is done at scale. There's probably people in this room doing Anycast at scale. Certainly my company does some. But it does take active network engineering. So that's Anycast. I mentioned that because we're going to go back to the story. This m.route servers, remember I gave all these list of IXPs that they're at. This is Anycast. There's one IP, well, one IP4, one IP6 address for m.route, and it's in all these locations. So we know they're doing Anycast. We also know San Francisco is the closest place to Denver. That's where I want my traffic going. And Comcast is sending it to San Francisco. Data center, it's getting to Paris, which is not close to Denver. And how did I determine Paris and San Jose? When I did the trace route, I saw SJC in the trace routes over here for Comcast. I saw which IX in Paris it was on in the host names from the data center. So I could make some inferences from that. These are guesses. I could be wrong, but I'm probably not on this because who would name their San Jose server after Paris? Probably someone in this room. So the server at the IXP in Paris, what's the relationship between that server on that IXP and Zayo? Well, it's an IXP, so it's going to be shared Ethernet. No money's probably exchanging hands here because if you were exchanging money, you'd want a service level agreement of some kind. No one's going to give you a service level agreement across a shared medium. So I know that server's probably a peer of Zayo in Paris. And then, okay, what's the relationship between the data center I'm at and Zayo? Well, there's only one possibility if this is a peer. Someone's got to be paying Zayo. So Zayo's got to be the transit provider. And I kind of set that up, and as you'll see why I mention this in a second. Comcast, on the other hand, and Lumen, and this is common knowledge, probably a peer between them. I'm going to put a question mark out after it because I don't know that either company has said for sure if they are, but I'm going to assume for this discussion that they are. Then it goes to this company called Regis, and then to the server. Regis is a Japanese company. m.route is a Japanese instance of this name server. So the server's probably essentially a customer of Regis. What's Lumen's relationship with Regis? Well, it's got to be a customer. This isn't a big enough network that a tier 1 internet provider would buy transit from them. So it's going to be a customer. And even if they did buy transit, they wouldn't carry the traffic for Comcast from a peer. So in this case, I know a little bit about these business relationships, or at least I can make some educated guesses. Could be wrong, but probably most of the time when you make these kind of guesses, you're probably going to be right. Why is it doing this, though? Again, why is my data center going this path? Maybe my data center also has Lumen as a second transit provider. Well, if I had Lumen as a transit provider, Lumen is the Lumen hop, the Regis hop, the server hop. So 3 hops, 3 autonomous systems. The Zayo hop, they're paying as transit. Zayo and the server, 2 hops. If they're paying Lumen and they're paying Zayo, they're paying both parties, so they're both going to be the same local pref. We're going to fall back to number of hops. So this is where it comes into practice. This is where you can start to figure out what's going on with the ISPs. One thing here you might say, okay, well, doesn't Zayo peer with them in San Francisco? Well, it doesn't appear that they do, just for whatever it's worth. And that's probably a business decision by Zayo. So what you've learned through this, I hope, is that BGP seeks the best performing path, but only if you look at what the accountants would consider the best performing path. Does not pay attention to geography, doesn't know anything about geography. You know that the traffic in both directions for a server to a client across the internet is probably completely different in each direction, may even go through different networks entirely. Everything on the internet, how it works, you have to understand the business relationships for the technology to make any sense. And then everything I presented is the simplified internet. The real internet is way more complex, including the business relationships. The business relationships roughly still divide into those 3 categories, but there may be nuance. If you're interested in the slides, there's the link. And I've given time for some questions, so if people have any questions.
Yeah. Your Zayo circling the planet to an Anycast, I think that Paris DNS server, they, for a preferred prefix or whatever list, they considered all of Zayo's IPs as equal cost. They didn't break it down to Zayo brands.
Right.
So then they told Zayo, we prefer from the priority list, not Zayo brands.
Mm-hmm.
Some companies, they don't want to analyze the list of IP prefix suffix ranges. The easiest way is just to click ASN, collect the entire list of IPs blindly, and then apply the same QoS request to it. So they're sucking traffic from all of Zayo planet Earth instead of Zayo brands.
Right. Yeah, and there is things that they could do where they could potentially tell Zayo only advertises in the market.
Zayo lives inside one office building somewhere on planet Earth. You don't realize they're like
Right.
5 continents with latency, so you think they're in a cul-de-sac. You don't realize they're a tier 1 ISP. You think they're a cul-de-sac provider.
Sure.
That doesn't do transit and is a dead-end tap. So you prioritize their entire IP range equally rather than asking for Zayo brands. I don't remember how you split up the ASNs because you got to split up the ASNs anyway, city by city. And
Yeah.
the ASN is just a bunch of IP ranges.
Yeah, from an Anycast standpoint,
You can't treat the ASN
yeah.
as a single office building with a latitude and longitude on planet Earth. It's not a single physical router you can take a photo of.
Right. But from a standpoint of doing Anycast, once that gets into Zayo, Zayo by default is going to propagate that globally. Now there is control over that, and you can, as a network engineer, say, no, this should not be propagated globally, but that comes with its own set of problems. And find me in the hallway, and I can explain some of those problems. I've got some good stories from that one. Yeah, go ahead.
So traceroute lets you figure out which server is on the way out. But
Right.
Is there any way to find out which servers the packet took on the way back?
No. It would make my life as a network engineer way, way easier if there was. What there is there's 2 tools that I'll rely on to troubleshoot Anycast. One is on network that I run. I have access to, it's typically NetFlow type of data, but it's essentially logs of the router of where do these connections come into. So I could see, okay, this is coming in the same place that it's going out, or no, it's not. It's coming in this other router port. But I can only see my network. I can't see anyone else's network. So the second place that I might go is maybe the ISP that I'm interested in happens to have a looking glass. That's getting more and more rare. But a public server where I can do a trace route from their network. Another option is something called Ripe Atlas, which if you haven't checked out, I'd recommend for anyone that's into geeky trace routes and such. Essentially, Ripe Atlas, Ripe is the European Internet Registry. They provide probes to people that are interested in setting them up on their network, and there will be probes in people's houses, just a little tiny box. And users of Ripe Atlas can then say, I'm interested in having everyone on this ASN trace route to my server, and I want to get what the paths are. That doesn't guarantee that the path from the user you're actually interested in is going the same direction, but it helps you troubleshoot. But yeah, it would be nice if there was a way of actually finding out that path. Yes, in the back.
So these relationships, these business relationships, cost relationships, do they ever have any dynamic bidding on those, or are the contracts a little more set in stone?
I don't do as much with the business side on negotiating the contracts, so I'm not sure. But I imagine that there's most of the contracts for most connections are going to be, I don't know if anyone's doing dynamic billing or not, but are going to be fixed. But they might have nuance. They might have nuance, like if you want to reach these destinations, it has one cost. You want to reach those destinations, it's got another. Time of day, those kind of things.
Did I miss it at the beginning? Why does a service provider pay for traffic? Because it's a cost for them. So when do they, I suppose, when they think somebody else will pay even more than they're paying?
Exactly. So if you've got, let's say you're starting up an ISP in rural area, farming area, and there's no ISP there, you want an ISP there. Well, how are you going to get to the internet? You're going to have to pay someone, because you can't just approach every internet company on earth and say, hey, give me free transit. You don't want to build out that infrastructure, among other things, and plus, they probably say no. So you're going to have at least one transit provider, probably two, because you want redundancy, to reach the internet. So that would become your route of kind of last resort. Then anyone that you could connect to with peering, that would be preferable. And obviously, if you could sell someone internet connectivity, that's even preferable to that. But yeah, you would have to charge more to your downstream customers than you're paying to your upstream. But hopefully you have enough farmers that want to buy internet that you can get some, you're selling them $50 a piece, let's say, and hopefully your upstream is cheaper than that at the aggregate.
This is all very much outside my bailiwick, but this is why I'm here. How does traceroute get the information if I can't see past the first AS?
Yeah, traceroute, what it does is every packet has a field called time to live. And every time a packet hits a router, that time to live is decremented. When it hits 0, there's a message sent back to the source saying,
So it's a failure message.
saying this failed and here's where it is. And if you see just stars in traceroute, then nothing's sending that failure message. But that's essentially how it works. This is normally used as a way of preventing loops on the internet. Otherwise, you'd have packets circling the earth forever, potentially, if routing was messed up. This keeps that from happening. Traceroute functions by sending first one with a time to live of just 1. And then that first router replies, then 2, and the second router replies.
It's a clever backhand fail like that.
Yes.
It's a clever manipulation here.
Yeah.
It's always there.
And was there a hand in the back?
Yeah, I just wanted to add something to complicate your question a little bit. So internet providers want to reduce their transit costs. Like that's their cost, except for like leasing lines and stuff. And so then that's why internet exchanges are so important. Because internet exchanges, you're basically paying for tool. So you're not paying like for the. So you want to plug into, if you want to find internet exchanges that make sense for you and plug
We're at most of them.
Yeah.
We're at the big
That's
ones.
probably gonna make up 80% of your traffic. And that's the value. So you want to peer with an interchange, and then you want to make, wait, sorry, when it connects to an interchange, then we start peering with, like whoever's on the other end of the interchange. And try to bring your costs down as much as possible. So that traffic is not free, it's pretty cheap, as opposed to dragging through an entity or something. But to the other question of trace route, if you have a app on phones, you can embed something there to send telemetry, which is extremely helpful. I won't say if we do that or not, but you have to know how to work for it. But let's just say that's an app. And we lots of hidden things in the background and send lots of very useful telemetry because it's helpful.
I want to add, some people have the opinion tier 1 ISPs are becoming obsolete because residential ISPs use internet exchanges and directly connected Cloudflare and CDN providers through direct peering links, because Cloudflare, Google, and Facebook will give anyone a free fiber link if you want to dump gigabits to your client eyeballs. So tier 1 traffic is slowly falling downwards unless it's corporate VPNs, because Google, Facebook, etc. do not want to pay ISPs. They'll give you a fiber link for free every week you remind them.
Actually, other feature, slightly bigger than the tiny ISP, they'll put servers in your traffic. So they won't just do fiber, they'll send you some.
They'll give you free equipment too. You just have to pay the one.
You just have to pay the cost of the traffic. That's usually cheaper than fiber. Depends on that's very complicated. Anyway, the big tech are evil is a fair sometimes thing. I'm not going to say that's whether or not, but they are trying to drive down.
Are there any other questions? Yes.
Can I get different latency for IP version 4 and 6, or are they using the same BGP?
It's a good question. Is IP4 and IP6 using the same BGP, or is it doing something different? It actually is using essentially the same BGP. There is some nuance there, but it's the same protocol. It's kind of remarkable that a protocol invented when it was able to be extended in that way and lots of other ways, but it has been. It is possible that the paths are different for V4 and V6 depending on all sorts of things. Like, for instance, if a network in the middle doesn't support V4, then V6 obviously, or doesn't support V6, V6 traffic won't route through that, for instance. But yeah, generally they work. This is protocol version agnostic, this presentation. Well, thank you for your time. And feel free to catch me in the hallway. I love talking about this stuff.